Hi everyone, welcome to this episode of Keipert Labs. In today's video, we're looking at part 3 of our series on constructing graphs, looking at trends and relationships. So, we're going to look at what is a graph. We're going to remind ourselves about what they're there for. We're then going to look at that idea of looking at the trend. What is the trend? Looking at showing trends in graphs, looking at a concept around graphs called anomalies, and then looking at how we can use a graph to make two different types of predictions called interpolation and extrapolation. All right, so what is a graph? A graph is a way to display data. Okay, we've looked at this before. Hopefully you've watched the two of other videos in this series about how we make a graph, how we use a scale for a graph. But the idea is that the graph allows us to see trends and relationships in our data. Okay, we can look at it, we can look at the information it presents, and we can understand something useful about these things that were measured in this experimental or whatever this thing involves. So we can see trends and relationships. But now that's part of what we're going to focus on today is, all right, well, what trends and relationships do we see? How do we see them? How do we make them? What's the purpose of that? Okay, but so if we look at this same experiment, this same graph, it's the exact same image that you're seeing now. We can look at this trend and we go, okay, as the added mass increases, so as we go from 0 to 50, 100, 150, etc., all the way up, the spring extension, the extension of the spring in centimeters also increases. Okay, we go, we've got a line that slopes upwards. It's going uphill. Okay, so that tells us something useful. It gives us some meaning to this experiment and also allows us to go those steps further to make predictions. We see, though, one thing that's important to notice is that this is what was called a linear or a straight line relationship. You can see that it's like going up a ramp where it's the straight line, it continues there. So that also gives us information about, about how these things are connected in scientific terms. It also then allows us to make more accurate predictions because we can see what the trend has been doing so far and how it's been doing it. Okay, but so now if we have a look at another set of data, okay, now there's no labeled axes here, that's not what this is about, but you can see these X's, these crosses represent the measured points. Now if we try to take the same approach to this one that we did to the last one and say, let's look for a straight line relationship, then it might confuse us. But we still need to know what the trend is being shown in this data. Okay, and it also, we need to be able to work out what kind of line should we be drawing in order to see that trend. So if we do a straight line like this, then you can see, yep, okay, so this is a linear relationship. But you and I can both see, hopefully, that this straight line is not the best way to connect this data. Okay, it ignores more than half of the data points. It only connects up or seems to relate to the first three. All of these other ones over here are nowhere near this line. And so it's not a really accurate way to show that pattern. Okay, so this situation cannot be a linear relationship. There's no way that we can take a straight line and put it through these points in any meaningful way that is an accurate thing to do. Even if we take the straight line and say, all right, well, let's kind of pick somewhere a bit more in the middle, then you've got points everywhere. None of them is close to the line. It's not the best way to go. But what about if we try for a curved relationship instead? Okay, so instead of going for a straight line, we go an increasing point here and then it starts to plateau off, and then we have these data points are very similar to each other. So it levels off to almost horizontal. This pattern fits the data much more consistently. It's a much more faithful representation of what's really going on here. Okay, and it also allows more accurate predictions, between these points and beyond. Okay, to actually say, all right, what happens if we keep going? What happens if we picked somewhere in between? What would we notice? What could we predict? Okay, and it comes down to that idea that trends in graphs, it comes down to whatever fits the data the best. So draw or choose the line that is being shown based on what fits the data the best. Sometimes a bit of trial and error is necessary for you to judge which way it is, which way it will look the best. Do we have a straight line relationship? Does it start, is it uphill? Is it uphill but doesn't start at 0? Is it downhill? Do we have a curved relationship that kind of increases, or it increases but levels off? Do we have the reverse relationship where it decreases in a curved relationship? Do we have some sort of an asymptote, which is the name for this kind of curve? Okay, whatever that might be, we have to go with what the data is showing us. It does not have to be a straight line. You don't have to mash it into a straight line relationship, because there's lots of things in nature and in science that are not expressed this way. Don't get hamstrung by the or thinking so rigidly that it has to be a straight line, or that you have to do this dot to dot kind of pattern because that's the only way that it shows anything. Okay, and it's also important to note that depending on the data that you have and what it means, what it represents, it may or may not be connected to the point 0, 0. Don't get attached to having to connect it to that point as well. You've got to think about, does that mean anything in the context that we have? So for the extension of the spring activity, 0, 0 has meaning, because we're saying that the spring has not extended because when we have no mass added. Now, the extension of the spring is how much further it stretches, not how long it is to start with. If we were doing that length, then it would not start at 0, because the spring is not 0 centimeters long. But the extension of it would be 0 because we haven't added anything to make it go longer. So it kind of depends on exactly what you're trying to show as to whether that point means something in your data. And so now we come to the question of saying, what happens if there seems to be a data point that doesn't fit the pattern? Something that's a little bit outside what everything else is seeing. We call those points anomalies, or an anomaly, singular, anomalies, plural. Okay, so you can see here that this point, this X point over there, is that's different to the rest. It doesn't fit the rest of the trend or the pattern. So what we do with anomalies is we identify them. We call them out. It's not about it making a mistake. It's not something incorrect. You don't necessarily know exactly what has caused an anomaly. Perhaps it might be something that you can correct for and you can try it again. Perhaps it's just a random error that can be introduced that, we don't necessarily know why. But we identify them and we don't include them in calculations or lines of best fit. We didn't adjust the line of best fit based on trying to go through and kind of account for this data point being one of them. We called it out and then we looked at the trend from the rest of the data. We excluded the anomalies. Anomalies are also often referred to as outliers. That is, data points that are outside the typical range for the rest of the numbers. Okay, so now we're going to look at two different ways that we can use our graphs to make predictions. The first type is called interpolation. Interpolation. So this is coming back to our added mass on extension of spring graph. Same graph, same image that you've seen a couple of times already. Okay, so interpolation is using the trend line on the graph, so the line of best fit, to predict values that would exist within that existing data set. We use the word interpolation because inter is referring to inside, like internal. Okay, so saying, all right, what if we added 220 grams? Well, we can find that value on this scale, 220 grams of added mass. And what we do is that then we use a ruler or a vertical line to read up to our trend line. And then we use our ruler to go across to our scale on our y-axis to work out, well, what would be the extension of the spring in this situation? We read it on the scale and we work out in this situation it would be 11.0 centimeters. Okay, so it's appropriate and accurate and valid for us to do this because we've established a relationship in the data already, that reading in between that, as long as our trend accurately reflects the data we do already have, is something that we can back that up. We've got evidence to suggest that this is what is going on, okay? Because we're using a trend that is already observed. But what about if we then look beyond? What about if we're trying to make trends or predictions beyond what our data already shows? This is called extrapolation. Extra being outside, like external. This idea of saying, all right, it's beyond the data set we already have. Now, the challenge is that it may or may not be accurate or valid to do this. There are plenty of situations where it is, but it doesn't necessarily hold to be true in every situation. You have to be a bit cautious and have to accept that you could be wrong in doing this. Okay? Because what it means is we're having to make assumptions about the trend, that the trend is continuing on in exactly the same way up to infinity or up to a certain point. And so then we're saying, all right, if we added 430 grams, then we're having to extend this trend line and then use that extension to then make an estimate about the data over here. But we're still having to estimate because we're still having to extend that trend line in a way. We're still having to assume that at this point that the spring is still going to behave the same way as it did down here. Now we know if this was a rubber band, that eventually you get to a point you'd extend it and then the rubber band would start to snap. Or it might get to a point at which it can't stretch anymore, and it's a different kind of force that's happening on it. So the straight line might not be justified. So we have to be careful about extrapolating beyond the data that we already have, because it may not work. Okay, as long as we can accept that, then we tread carefully. All right, so look, we looked at what is a graph, ways to showcase data, to see trends and patterns. We looked at the different trends that we can see. Okay, and being able to actually look at comparing the variables, being able to make statements and conclusions about what the data is showing us. We looked at this idea that trends in graphs, it depends on what the data is showing. It may or may not be a straight line relationship. It doesn't have to involve the point 0, 0. And so we just go with what the data is showing. We do a line of that best fits the data that we have, so that we can clearly see it. Any points that are outside or don't seem to fit the rest of the trend, or are significantly different, we would call anomalies, and we exclude them from what we do next, because they must be something about them that doesn't fit the rest. And looking at how we make predictions either within the existing data, interpolation, or outside the existing data, called extrapolation. All right, thanks very much for watching. Don't forget to like and subscribe. Bye for now.